Hi, this is Amar Agrawal from Department of Mathematics, BITS Pilania, Hyderabad campus, India. First of all, I would like to thank the organizing committee for giving me this opportunity to present my work here. I will talk on the dynamical stability of a bouncing cosmology in extended gravity. This work has been done with the collaboration of F. Taylor Ortiz, Deodatta Mishra, and S.K. Tripathi. In this work, we have studied the matter bounds cosmology in modified FRT gravity theory. This is the outline of my presentation talk. I will start with the introduction in which we will see why there is a need to study the bounds cosmology. Then we will see the formalism of the field equation. Then we will analyze the dynamical behavior. We will analyze the behavior of the dynamical parameters along with the energy conditions. Then we will see the behavior of the cosmographic parameters. And at the end, we will see the stability of the model. And then we will discuss our results. As we all know, the present observational data study state that our universe is expanding, and the expansion of the universe is in an accelerated way. The rate of the expansion can be determined by the time evolution of the scale factor. As we mentioned here, this universe is expanding. If you go back in a time, there might be two possibilities. The scale factor becomes 0 at certain time, or it acquires its minimum value. If the scale factor becomes 0 at a certain time, the Christmas scalar diverges. Since the Christmas scalar is inversely proportional to the fourth power of the scale factor. And the Christmas scalar is the only scalar which we got by the contracting the which generally measures the curvature of the spacetime. Hence, the violation of the Christmas scalar implies the curvature singularity. To avoid this is the case occur in the inflationary scenario. To avoid such an initial singularity, the quantum theory of gravity has been suggested. But we don't know what is the correct quantum theory of gravity. Hence, in the absence of the fully accepted quantum theory, gravity, the bounce cosmology is the most promising one that allows us a non-singular universe. Since, as we see above, this scale factor acquires its minimum value. This point is called as a bounce. And there are three conditions on the scale factor to get a bounce universe. The scale factor should not be 0 throughout the evolution. At a bounce epoch, the derivative of the scale factor with respect to cosmic time should be 0, and its double derivative with respect to cosmic time should be positive at a bounce. There are many bounce models are proposed in the literature like symmetric bounce model, exponential bounce model, cosine hyperbolic bounce model, matter bounce scenario is also there. Among these, the matter bounce scenario is the most popular. It leads to a late time matter dominated area. However, this matter bounce scenario suffers from the following two. First one is the anisotropic issue, and second one is the explaining the late time dark. We want to discuss the stability of the model. We'll see at the end. Here we are considering the non-singular scale factor a of t as alpha by chi plus t square raised to power 1 by 2. Here alpha and chi are two positive scale factor parameters. We have analyzed the behavior of the scale factor and the Hubble parameter for three different values of alpha that is considered to be 2.1, 2.2 and 2.3. It is analyzed that in the early time, the scale factor is in the contracting mode. Process is passes through its minimum value, and again in the positive time zone, it is expanding. While the Hubble parameter showing negative behavior in the negative time zone crosses 0 at a t equal to 0 and showing positive behavior in the positive time zone. Now, our aim is to get the stable behavior of the universe in the modified FRT theory, gravity theory. Hence, we are considering the action equation for the FRT gravity theory as in equation 1. Now, the field equation for this FRT gravity is defined in equation 2. There are three different models suggested in the FRT gravity theory, like R plus 2ft, F1R plus F2t, F1R plus F2R into F3t. Among these three, we have considered the R plus 2ft, such as R plus 2 beta t plus 2 lambda. And the line element is considered to be line element is considered to be FLRW space-time, which is defined in equation 3. Now we are considering the fluid to be perfect fluid, and the energy momentum tensor for that is defined in equation 4. Now the field equation for this FRT gravity in the form of Hubble parameter are defined in equation 5 and 6. Now for our convenience, we have considered the value of eta is equal to 8 pi plus 3 beta. Now the dynamical parameters like pressure, energy density, and equation of state parameter are respectively represented in equations 7, 8, and 9 respectively. We have also analyzed the behavior of the pressure, energy density, and equation of state parameter for these three different values of scale factor parameter. We found that the pressure is showing negative behavior throughout the evolution, while the energy density shows positive behavior throughout the evolution of the universe. Also, we have noticed that at a bounce epoch, the pressure is showing pressure acquires its minimum value at a bounce epoch, while the energy density fails to acquire its maximum value at a bounce. It has a small bump at a bounce, while the equation of state parameter shows phantom-like behavior, and it as we move from this bounce epoch, it crosses lambda CDM line and showing continuous behavior throughout the evolution. Moreover, for three different values of alpha, the equation of state parameter shows approximately equal behavior, same behavior. Also, in the context of a GR, if the Hubble parameter goes to 0 at a bounce epoch, it means at a bounce epoch, the null energy condition should be violated. While in the modified theory of gravity, like FRT gravity theory, we have analyzed the behavior of the energy conditions, and we found that the null energy condition is violated at a bounce epoch, while the strong energy condition violated throughout the evolution of the universe, and the dominant energy conditions fails to be violated. Also, we have calculated these cosmographic parameters, jerk parameter, snap parameter, and snap parameter. This parameter we can get from the second, third, and fourth derivative of the scale factor with cosmic time. And it has we also plotted the graph for this cosmographic parameter, and it is analyzed that at a bounce epoch, all these cosmographic parameters shows singular behavior, and as we move away from this bounce epoch, all these cosmographic parameters approaching to nearly value 0. Not exactly, but they are approaching to 0. Also, we want to study the stability of the model. Hence, we are considering the pressureless dust FRW background, whose general solution is H at T naught is equal to H0 P. And there is a small deviation in the Hubble parameter, which is denoted by delta, and the delta mt denotes the small deviation in the energy density. Using the perturbative approach equivalent to FRW equation, we obtain this equation 14. And for the above bouncing, for a bouncing scenario as prescribed above, we obtain the geometrical perturbation and the matter perturbation respectively represented in equation 15. Now we have plotted this graph for this deviation in the energy density versus cosmic time, and the deviation in the Hubble parameter with respect to cosmic time. We found that at a bounce epoch, both this graph shows maximum behavior, and as we move from this bounce epoch, they are decreasing, and they are reaching to the value 0. The decreasing behavior of these perturbations shows the stable behavior of the universe. That is our aim. In this paper, we have discussed the matter-bound scenario in the modified FRT gravity theory. Also, from the scale factor and the Hubble parameter behavior, we have noticed that the bounce was happen at a t equal to 0. We also found this dynamical behavior of this model, and from this equation of state parameter, we have analyzed that at a bounce epoch, the equation of state parameter shows phantom-like behavior. However, as we move from the bounce epoch, it passes through lambda CDM line and showing continuous behavior throughout the evolution. Another criteria for the bounce cosmology, especially in the GR, the violation of the null energy condition. Same thing we have obtained in the modified theory of gravity, like FRT gravity theory. We obtained, we analyzed that this null energy condition get violated at a bounce epoch, while the strong energy condition violated throughout the evolution of the universe, and the dominant energy condition fails to be violated throughout the evolution of the universe. We have also found this behavior of the Hubble parameter and other cosmographic parameters, and it confirms the bouncing scenario of the universe. On the stability features of the model, we have observed that the model remains stable throughout the evolution, and that includes the bouncing epoch also. However, it is scope to study the matter-bound scenario with late time cosmic acceleration. Thank you for your attention.